All right. It's on. Let's get started. So it's my pleasure today to introduce our colloquium speaker, Chris Fiacconi. Chris is a former graduate student from our program. He finished his PhD in 2012, then went and did a postdoc at Western University, and followed that up with landing a tenure-track job at Guelph. It's remarkable that you've been there 10 years now or something like that. And at Guelph, Chris has broad interest in experimental psychology. And just to give you a sense, he spent some of his time here doing visual psychophysics with Pat and Allison. His interest in some of the methods of visual psychophysics, signal detection theory, you can still see in his work that's now aimed at higher order cognition. He has interests, he does work that touches on attention, working memory, computational issues in memory, and then a topic that I'm sure is going to come up today will be meta-memory, and I'll let Chris describe what that is. Let's see, sometimes, you know, introducers think of a fun fact to tell about the speaker, so I thought I'll try to do something like that, but given the nature of the talk, I'm going to make it a fun memory, right? And digging further into it, this is me now reaching back into history, trying to come up with a fun memory about Chris that could be true or could be just a figment of my imagination. And so it'll be Chris's job to tell me whether this fun memory is indeed a true memory or whether it's a false memory. So I vaguely recollect that when Chris was a graduate student, the graduate students yearly threw a big Halloween party. Wasn't that the case? Oh, yeah. Yeah. Right. Now, faculty, I suppose some faculty, I never attended that party, and I didn't this year. But I later came back to the department the following week and heard that Chris, and this is my memory anyway, that Chris had gone to this Halloween party dressed as me. Okay, Tris, is that a true memory or is that a false memory? That's absolutely true. Remarkable. Okay. I won't bore you with any more details. After the talk in our reception, you can scratch your head. How would you dress up as? And there is a clever thing that he did that I think I remember, but we'll deal with that after the talk. Without further ado, then I will pass the floor over to Chris.
Okay, I think it's working. So when I flick it back to, oh. All right, I'll try this. Is that better? Okay.
Where was I? Okay, so I was on sabbatical, and I wanted to order this book, and so I went on Amazon to buy it, and they didn't have any new copies. They only had a couple of used copies for sale on Amazon, so I said, well, that's fine. I'll buy a used copy of it. So a couple of days later, it arrives in the mail, and I open it up, and I flip open the very first page of the book, and turns out that it's none other than Lorraine Allen's old signal detection books. So for those of you who may not know who Lorraine Allen was a faculty member here in the PNB department for a number of years. Unfortunately and sadly, she passed away in 2012. But she was quite active in the field and did a lot of influential work as part of her faculty position here. So I just thought, well, as much as I'm still in contact with people from McMaster today, it seems like McMaster still follows its way with me as well. So I just thought I'd sort of share that little funny tidbit with you. All right, so what I'll do now is maybe dive into a little bit more of the focus of my presentation today. And I'll start sort of with a bit of a scenario, okay? And I call it the parable of the disappointed student. This here, we'll say his name is John. And John is disappointed. He just finished a very heavy midterm exam, and he didn't do as well as he thought he did. He left sort of feeling pretty good, feeling pretty confident that he was going to do well, and when he got his mark back, he was quite disappointed, and as you can see here, a little distraught. So one of the things I'm going to be talking about to you today is why this happened. How does this happen? Why is it that sometimes people can be quite confident in their performance or in a memory of some sort, but nevertheless be wrong? And this question, I think, begs for a consideration of something what we call in the literature the topic of metacognition. That is our ability to think about our own thinking. So we have our first order thought. You want to think of it as sort of like our ability to think, okay? So we call this the object level. And I'm going to use the framework developed here by Nelson and Narens. I think it's good for some things, but a little sparse in some areas. Nevertheless, we can think of the first order thinking as basically what we come to know as cognition. So we can think of it as mental computation. But of course, as humans, we can think about our thinking, and we call that process metacognitive monitoring, okay? And think of it like the assessment of how well sort of our current train of thought is suited to meeting our goals. Now, we can also, if things aren't going according to plan, we can intervene, okay, via metacognitive control. And we could do something to ensure that we change course such that our thoughts are sort of more aligned with sort of our goals and what we want to accomplish. So that's sort of a real sort of basic, I guess, it captures sort of how metacognition researchers generally think about the relationship between cognition and metacognition. But today, I'm going to sort of hone in a little bit, and we're going to replace these two terms here and focus a little bit on the domain of memory. How do these concepts apply within the domain of human memory? And I'll talk a little bit about some work that tries to connect these things and maybe offer a slightly different perspective on it. But what do I mean here? So when I talk about memory, you might be thinking, well, what's the difference between these things? By memory, I'm really referred to the kinds of mnemonic processes that occur unintentional, or not unintentionally necessarily, but automatically, things that don't require sort of intention. So you can encode information without trying to encode it, right? There are processes, neurobiological processes that allow that to happen, things like hippocampal pattern separation, that kind of thing. And I'm also referring to retrieval, that is the sort of the recovery of information from memory that was stored during encoding. And the term for this that was used by Endel Talving sort of back in the 80s is he had a special term for it, he called it ekphory, but basically it was just the rousing of memories in the mind by some cue in the environment. And that process is what we call retrieval. And when I talk about metamemory, I'm really sort of referring more to things, or at least the field, generally speaking, would refer to metamemory as strategic. It's more volitional and willful in nature. You can, like I said, kind of act on sort of the lower level first order thought processes in a sort of strategic or thoughtful way. And it's kind of also, I like to use the term learner-centered in a way. And by that I mean it invites consideration of the ways, all the ways in which learners sort of bring their idiosyncratic experiences to the table, to the learning environment. And we can sort of learn a lot by sort of asking people what it is they're doing and taking into account the fact that there are some idiosyncrasies there that are theoretically interesting, okay? So these ideas kind of caught the attention of even the late, unfortunately, the late, great Endel Telving back in 1970, who I thought this quote kind of sums it up kind of nicely. And when I stumbled upon this, I thought, wow, that was interesting. And I actually stumbled upon this while I was a graduate student here, and I thought this is kind of an interesting quote, but I was busy doing other things and I didn't really have a chance to follow up on it. But when I started my position at Guelph, I thought, this is a good time to sort of return back to this issue. And so this quote, why not start looking for ways of experimentally studying and incorporating into theories and models of memory one of the truly unique characteristics of human memory, its knowledge of its own knowledge. We cannot help but feel if there's ever going to be a genuine breakthrough in the psychological study of memory, it will, among other things, relate the knowledge stored in the individual's memory to his knowledge of that knowledge. So I thought this was great, and when I came upon this quote, like I said, I was interested, but then I was thinking, man, this is a great quote to use for a presentation. So it really sort of highlights the sort of importance, in a way, of meta-memory. If it catches the attention of Endel Telving, it probably will catch the attention of others, too. So I started to look at this in a little more detail, and the work I'm going to tell you about today sort of tries to unpack this a little bit, okay? So I'm going to sort of focus in on these monitoring and control processes and tell you a little bit about some work that we've done, trying to understand how they work. And what I mean by that, by work, I mean they can sort of operate in two sort of areas of memory, right? We typically think of memory encoding and memory retrieval as sort of separate points in time. There's some acquisition of information, and then there's the sort of the recovery of that information that happens later. And I think monitoring and control sort of operate at both of those time points. So as a little sort of a rough guide for the presentation today, I'm going to sort of be returning to this 2x2 grid, and I'm going to tell you a little bit about work that we've done in sort of each of these four quadrants. But just to start, let me give you an example of how meta-memory might sort of work its way into each one of these cells. So for example, at encoding, we can implement control by virtue of engaging with different mnemonic strategies, ways of processing information, unique things of linking bits and pieces of information together to make things memorable. And of course, the things that work for me might not work for you. This is also sort of invites that learner-centered idea that I discussed previously. When we talk about memory retrieval, we can talk about control by, for example, people can use information from memory to strategically, they can use that information strategically, okay, to identify new things or detect novelty. So an example of this would be recollection rejection. That is, sometimes I can recall information that then I can use strategically to reject or declare that this thing is not something that I've seen before, but rather is novel. So we would consider that sort of a control process, because people using the information in a strategic sense, okay, to identify novelty. We can talk about monitoring during encoding. For example, how is it that people assess the memorability of the information that they're encoding or that they're trying to learn? And we can also talk about monitoring at retrieval. For example, okay, how do we know whether or not what came to mind is actually correct? How well can we monitor or assess the veracity of the content that comes to mind? And this is closely related to things like confidence, okay? And where does confidence come from, and how does it relate? So this is sort of just a few examples of the ways in which sort of meta-memory can color all of these different sort of cells in this 2x2 grid. And I'm going to sort of start off by sort of focusing today on these questions. So first of all, does affording control benefit encoding? If we allow people, we give them some autonomy at the time of encoding, do they benefit from that? Okay. We're then going to ask, can people strategically avoid false memory? Okay, and we'll talk a little bit about the idea of recollection rejection and some novel applications of it. And then what informs memory prediction? So what information are people using when they're trying to predict what they'll remember later? And then finally, how do we perceive and act on the veracity of our memory? So I'll sort of start off with the first question here, okay, and tell you a little bit about some work there. Push a key and then move on to the next item. In experiment 2, we did a sort of a slightly different one. What we did was we gave people a few different strategies that they could use, and we said, use whatever one you'd like to use, okay? And we want to know if affording them that control is associated with any kind of mnemonic benefit. So I'll focus in on experiment 1 here. This was work done by my PhD graduate student, Anna Kazachkova. And the experiment, it's a fairly simple design. It's basically 2 groups. Okay, we have what we call the self-paced group. That's the group that got the control. They could simply self-pace their way through this list. So for example, they might spend X amount of time on each item. But then the control condition that we wanted to compare the results to is what we call a yoke control condition. So for every yoked person, they had a counterpart in the self-paced group. Okay, and then they saw each item, all the same items, in the same order for exactly the same amount of time. So the encoding experience on some level was identical for both of these conditions because everything was held constant. The only difference was that in the self-paced group, they had the ability to control. Okay, and you might think that the ability to control time here might help them tailor sort of their encoding to their own idiosyncratic needs, and that might afford some benefit.
Mic went out again. Could you use the?
Oh,
Sorry.
sure.
Sorry. It's full battery now.
Oh, it is. Okay. Okay, is that better? Okay. All right. Two identical, in some sense, identical sort of encoding experiences, but we want to know what's the influence of affording people autonomy in a self-paced group. So I'm going to show you the results from an experiment like this. These are the 2 encoding conditions. Now, we also gave both groups a test, simple recognition memory test, where they were given all of the items that they've seen before as well as an equal number of new items, and they just have to simply say, is this one that I've seen before or not? But we kind of made it slightly more complicated. We got them to rate their confidence. Okay? So on a scale from 1 to 6, with 1 being sure that this is a new item, and 6 being that sure that this is an old item. And what this allows us to do is to sort of leverage a technique that's borrowed sort of from the signal detection literature. And I'm going to sort of outline that a bit here so that some of you might sort of already be familiar with this, some of you maybe less so. And so I thought maybe it'd be a good opportunity to maybe do a quick crash course in this. But to analyze the data, at least in studies like recognition memory, it's often we often employ what's referred to as the signal detection framework. And in this framework, you can think of the x-axis as representing something like memory strength, okay? And that old items, which I have in the solid line here, will on average elicit sort of a greater familiarity or strength signal than the new items, and that's why the distribution is shifted. But the point is that both old and new items will vary in the degree of familiarity that's elicited, and even the new items will sometimes feel quite familiar and sometimes not so much. All right, and so you can think of people using a confidence scale sort of in the following way, where people just simply place 5 of these criteria along the x-axis, and to the extent that on any given trial, the familiarity signal exceeds any one of these confidence criteria, people will give that number as their confidence rating. So for example, if on a given trial, let's say an old item appeared and it had this level of familiarity strength with it, the person would assign that probe or that memory item as a 6, okay? Now, as you can see here, most of the time, the 6s will be associated with old items. That means they're going to be correct or make a hit, okay, much more often than they're going to make a false alarm. So what we can do is we can use these different confidence ratings to plot what's known as the receiver operating curve. This receiver operating curve is just a cumulative plot of the hits and the false alarms across each of the 6 confidence bins, okay? So we would have some proportion of hits associated with 6s, a little bit of false alarms associated with those 6s, and we can do the same thing for the 5s, the 4s, and the 3s, the 2s, and then we just add them all up, and we get the 5 points on our RLC curve. So what I'm going to be showing you then is the data from both of those 2 conditions, but I'm going to show you first what the RLCs look like when you plot them. So here we have hits again on the y-axis, false alarms here. Now, better discriminability, in other words, better memory discriminability would be reflected as a higher ROC curve, okay? So when we have our 2, we can plot them for each condition, and you can see that the self-paced group does indeed demonstrate better recognition sensitivity. So affording them control of study time does appear to benefit them to some extent in an experiment like this. And then we can also, for conventional statistical analysis, we might want to derive sort of a measure of discriminability for every participant here, which we'll call DA. And we can do that, and we see, again, a very sort of robust
effect here, and we've been able, fortunately, to replicate this a few times, which is sort of nice to see. But I'm going to sort of move on now and talk a little bit about giving people control over strategy choice. So this was work that, again, Anna has done in sort of tandem with my honors thesis student, Sarah Elkins. And we gave people a choice here. We familiarized them with 6 different strategies that they can use to encode the information. So, for example, they could read each word aloud as it appeared. They could create a sentence using the word. They could, think about it sort of in a way that connects it to themselves, self-referential thinking. And what they did was up to them. They just had to self-report after each trial during encoding which one they used. And, of course, we have a similar design that we did before. So we have what we call the strategy choice group. Okay, so the strategy choice group, as it sort of sounds like, they have the choice of which strategy to use. And we can compare that to the strategy yoked group. All right, the strategy yoked group, again, okay, they're going to use whatever strategy was used for that participant for that item, okay, in the same order. So again, we're trying to equate the study experiences for both conditions, and then we can look to see if affording them that choice, okay, benefits memory.
Is it only those 6 options they have?
Yes. No, it's only the 6 options. We have to limit it to some extent, just because we need everybody on the same page with what each strategy means, so that when we ask somebody to do it, they have a sort of an accurate picture of what's being asked of them.
And within the experiment, was they use the same strategy for the whole experiment, each participant, or it could vary on
Oh, no, yeah, so whatever they use on this particular trial it could be the same as the one on the previous trial, it could be a different one. It's just whatever they did, okay, they just have to self-report it by picking the one out of the 6, okay? And then whatever they chose, the yoked participant would have to do that same thing. They were just instructed to do it, though, instead of giving the choice to do it, okay? And what you see in a situation like this is a similar benefit, okay? So here's the ROC curve, and then we have our mean discriminability here plotted. So again, it seems like affording learners autonomy, okay, is a good thing for encoding, and that learners can somewhat intelligently tailor their encoding to their idiosyncratic needs. Because in this sense, right, the only way that somebody could benefit from control, assuming that there were no other differences in overall study time or things like that, it means that they are sensitive to sort of what works for them, and by doing that, that allows them to sort of maximize their performance. All right, so I'm going to move on now, and this is where the false memory sort of part of my title comes into play, and tell you a little bit about how we can sort of use memory retrieval sort of strategically to perhaps help us detect novelty and avoid false memory. Okay, so memory is not perfect. This is not news to anyone, okay? But it's often, it's correct more than it's not, okay? But nevertheless, the ways that it fails are important in that they reveal sort of the structure of memory, and we can learn a lot by looking at the way that memory fails. And perhaps the most sort of famous illustration of memory failure could come from what's known as the Dease-Roediger-McDermott paradigm. So this is a task you probably are all familiar with. It's sort of in introductory psychology textbooks, right? You get a list of related words like this: queen, prince, king, royal, etc. And then at test, you see all of the words you studied before, but I throw in an extra one that you never saw, but it's highly related to the list. We call that the critical lure, something like crown in this case. And what you generally find is that people will not only claim that they studied crown before, but they will often claim that they falsely remember it. It's like, I have an image of seeing crown on the screen, like it was definitely there. And it's that aspect of false memory that's intrigued people in this phenomenon for a long time. But at the same time, you might think, well, that's kind of odd, right? Why does this happen? You can sort of intuit in some sense that all of these things are highly similar, and so that therefore when crown appears, you get a very strong familiarity or memory signal that gets returned that leads you to say that this is an old item. But why isn't it the case, if people have good memory, why isn't it the case that they can just simply recall the ones that they did see, and then by virtue of elimination, reject crown as having not been studied? Now perhaps it's a memory load issue in that there's just too many items for people to remember in order to do that, and they of course don't know exactly how many from each category were present, but nevertheless it remains a possibility. So this is the sort of the gist of where we're headed here with experiment 3. To what extent can we strategically use memory to mitigate false remembering via this sort of recollection rejection process? And sort of a sub sort of question that we wanted to address here was, might reminders facilitate novelty detection? What role does reminding play in this? And this is work that's sort of been done by Catherine Chury. She's sort of my most senior PhD student now. So what we did was we modified the DRM slightly, okay, to allow us to answer this question. And what do I mean by reminding? Well, I mean, you get a bunch of related items coming to mind, or being shown to you, okay, in a list like this. You might think that certainly sometimes people will get to king and say, wait a minute, that sort of reminds me of queen. Didn't I see another royal-related word sort of in here? And what are the consequences of that reminding procedure? Might that reminding, that spontaneous reminding, could something like that happen? And then if it did happen, to what extent might it facilitate recollection later on, which would then help us reject the novel lure, in this case, crown, okay? So we used the modified DRM procedure. I like to call it the DRM light because we didn't use, 10 or 15 semantically related list items. We used 2, okay? To make it a little bit feasible. We had pairs of items. We had 18 related pairs, so this would be like queen and prince, for example, as well as 18 arbitrarily paired words that we made sure of that weren't actually all that related, so like glass and winter, okay? And they were just presented one at a time. And for every item, as it appeared on the screen, okay, we'd have them all intermixed, and there'd be some lag in between each member of the pair, okay? So it wouldn't all be sort of like back to back. But every item, we asked them a question. And the question was simply, does this word remind you of an earlier item? Okay, is this in any way, shape, or form? And if they say yes, we then ask them, well, what word did it remind you of? Right? So, for example, they might get to prince, and then if they're asked the question, they might say yes, and then, that reminds me of queen. So what this allows us to do is to then break down the data later on when we get to test, and we start showing them those critical lures. They might get a critical lure like crown, and then we can conditionalize the false alarm rate to crown based on whether or not they reported reminding of the related pair at study, okay? And if reminding here, okay, boosts or helps with them recollect both of those items later on, then we should be able to sort of see that they're protected on some level from endorsing crown as having been studied before, okay? So at test now, we also ask them for every item. First of all, is this an old or new item? All right, just a recognition memory test. We have our related and our unrelated lures. And the second question we ask is, does this item remind you of anything that you studied before? This is your opportunity to tell us, okay, did crown here, what studied items were associated with it, okay, if you can. And we can then conditionalize the data further based on what the test response is, all right? So they could say nothing, and we'll call that the no remind condition. They could say something, crown reminds me of something, but I don't remember, okay? We'll call that the remind only. And then they might be able to recollect one member of the pair. That would be the remind rec 1. Or they could get both, in which we would call that the remind rec 2. So what we're going to do is we're going to break the data down conditionally based on the responses to these reminding probes and see what the data look like. So what I have plotted here are the false alarm rates, all right? So the gray here are the unrelated lures. So these would be new items at test. But they're not related at all to any of the items from study. And then the black dot here, this is our related lures. So we see a bit of a DRM effect here. Well, it would be weird if we didn't, right? It's a very robust finding. It's not a huge effect, but that's in part because we only had 2 related items. Really what we want to know is what happens to the false alarms when we conditionalize, okay, these false alarms to the related lures based on those probe responses. So what I'm showing you in this plot here is when we're reminded of the related study pair, okay, at study. So that would be, for example, going back here, that would be an example where the lure at test would be crown, okay, and it was associated with prince and queen. And when they saw queen and prince during study, they were reminded, okay? So that's what we're talking about when we talk about this graph. Reminding at study had occurred. Now, what are the consequences for false alarms at test? Contingent on what the test response was. So we can start by looking to see what are they when they were not reminded at test, and you can see we have a moderate level of false alarms. When they're reminded only, okay, you get this sort of boost, meaning that, well, it's a bad boost, right? Your false alarms are increasing. And we think what this represents is a sense of familiarity for these items. Obviously, it reminds them of something, But because they can't recall what it was they were reminded of, it's familiarity that's left unchecked, okay, in some sense, by any kind of countervailing force that might help them reject that novelty. In other words, we think of this as familiarity without any recollection of the details that might help them eliminate or reject that item. Now, we can consider also the remind rec 1 condition. That has a lower level of false alarms associated with it, which you might predict. But maybe what's most interesting is the remind rec 2 condition. And when they're able to recall both of the related studied items, okay, their false alarms are no greater than that for the unrelated lures. Now, you might be thinking, Chris, you're doing a presentation, maybe you should make sure all your points are the same size before you get up in front of everybody and start talking. But I tell you that's done because the size of the points here represent the proportion of times those conditional responses happened, okay? In other words, people didn't actually recall both of the related studied items very often. That's why this point is so small. Most of the time they were able to get one, okay? But they didn't do this very often. In fact, it only happened about 12% of the time. But when it did happen, their false alarms were quite low. Now I'm going to show you the data what happens when they were not reminded at study. Okay? So when they're not reminded at study, I can't even plot the rec 2 condition because it never happened, like 1% of the time. Okay? Meaning you can't even get a reliable estimate of false alarms in that condition. Why? Because no reminding happened at study. Reminding, if you think about the process of reminding as begetting recollection, and recollection begets novelty detection by virtue of recollection rejection, okay, then it makes sense that we can't even plot that in this situation. And in fact, we don't even see any reliable difference between these three conditions here when they were not reminded at study. Okay? So that's sort of a nice illustration that at times, under some situations, people can recall information and use that to reject novelty and avoid making a false alarm to a critical lure, a false memory. And that reminding seems to play a role or help with that process. Now, of course, this is all nice and well, but you'd like to see it again, right? So we looked for some converging evidence using a slightly different approach. And we wanted to use that ROC approach that I talked to you about before. But this time, we're going to do a little twist on it. It's not going to be your standard ROC where we plot hits on the y-axis and false alarms on the x-axis, okay? This time we're going to do something a little bit different. And we sort of took this approach from actually a talk that I saw at Psychonomics in November by Andy Ionelinas. So Andy Ionelinas is sort of very well known for his work with ROCs and recognition memory. And he developed sort of a novel ROC approach that he calls it the FROC, for false memory ROC. And in this case, he's going to do something a little bit different, but the theoretical underpinnings are as follows. So in a sort of a false memory paradigm, right, we have our similar lures, those are our critical lures, and we have our completely novel items. And by virtue of their similarity to studied items, okay, the similar items, generally speaking, the similar lures, that's the dashed black here, will be a little bit more familiar than the new items, okay? But importantly, there's sort of two other things happening here. Namely, sometimes, with some probability, we can recollect, okay, a similar lure will elicit recollection, okay, of veridical details. Like, for instance, crown, eliciting recollection of queen and prince. And the recollection of those veridical details will then allow us to confidently reject that item. Okay? That will happen with some probability. However, sometimes the process won't go so well, and the similar lure crown might bring to mind false details or recollection of false information that makes them believe that I remember seeing that item on the list. So in other words, similar lures have this sort of double-edged sword thing going on, right? On some level, they can elicit veridical recollection, okay, which helps you reject them, but at the same time, sometimes you pattern complete and you have a false memory or a false recollection of having seen that before. Now, if we look at the ROC and we simply, instead of plotting, for example, hits and false alarms, what we plot is on the y-axis, we plot false alarms to similar lures, and on the x-axis, we plot false alarms to novel lures. Okay? The shape of that ROC tells us something about the contribution of these three processes to performance. Okay? So you might think that the responses could look something like this. To similar lures, okay, there's a bunch of sixes, okay? Maybe one sort of six to a new item, to a completely novel or a non-similar lure. And so this is an example of how the responses might be distributed. And if you were to make an ROC from these responses, it would look something like this. And it's a little bit different looking. And there's three sort of key parameters that you can derive from an RLC like this. One is the y-intercept on the left, and that y-intercept will represent or index the degree to which false recollection has occurred. The curvature, okay, of the RLC is a measure of false familiarity. That is, to what extent are these two distributions separate from one another? And here we have sort of this novel aspect here, which is the right y-intercept, which represents, okay, the degree to which recollection rejection had occurred. So that's, again, these are similar lures that elicit veridical recollection, which then affords highly confident rejection, correct rejection in this case. Okay, so, and you can measure these three, contribution of these three processes by simply looking at the shape of the RLC. So the only real difference that we needed to do for with our paradigm that I described to you just a minute ago was to add confidence ratings so that we could create these RLCs. So that's what we did. And what I'm going to do is I'm going to show you sort of what the RLCs look like, but I'm going to make two of them. One, I'm going to plot what the RLC looks like when people were reminded at study, that is, okay, Queen elicited reminding of Crown, okay, or not reminded at study, that is, Queen did not elicit reminding, of Prince, not Crown, Prince, okay? And when you do that, okay, just a reminder here, this is what the three key parameters that we're looking for. You can see that the data sort of fall in line with what you might expect. When people were reminded at study, you see that the y-intercept on the right here is lower. Again, suggesting that reminding supports recollection, which then they can use strategically to reject the novel lure. Now, you might be thinking, well, that's strange, though. There's some recollection rejection happening as well for the not reminded at studied items. And didn't you say that they almost never were able to actually recall both items? And that's true. And what we think might be happening is that even though, for example, people often recall only one of the two items, they can nevertheless they might be trying to use that information as a way of disqualifying the item. They were never explicitly told that there's two items from every category. And so if they recall one, they may figure, well, it's better than nothing. It probably means this is a new item because I can recall one of the related items and it wasn't that one. It wasn't Crown. Okay, so I'll still confidently reject it. So we still need to do a little bit of further work to sort of verify that sort of hypothesis. But the key result here is that this y-intercept is lower than this y-intercept. Again, suggesting that reminding supports recollection, which is then used strategically to avoid false memory. Okay. So in summary here, reminders can facilitate use of recollection rejection, okay, and they help us detect novelty. All right, the next sort of section here, I just want to talk a little bit about what informs memory predictions. How can we consider the sort of this bottom left cell here, monitoring during encoding, okay? So sort of a basic fact that is true in the literature is that at study, people can somewhat accurately predict what they will later remember. And this is a project that sort of was worked on by my former PhD student here, Skylar Larson. And the question is, how can they do this? Why is it that they can somewhat predict what it is that they'll later remember? It's not great, but it's definitely above chance, and it's definitely reliably above chance. So what information are they using to do this? Now, the sort of the old school of thought on this is something what we would call the direct access view, which simply states that learners have somehow, once they encode some information into memory, they can access the vertical strength of that encoded trace. And they simply read out that strength value, okay? And if it's a strong trace, they make a strong prediction, okay? So they predict, yes, I will remember that later on. And if it's a weak trace, they'll say, no, I won't remember that later on. And of course, to the extent that what they're accessing is veridical information, you would expect that that would support a link between their predictions and their later subsequent memory. However, the problem with the direct access view is that it always predicts this alignment between memory predictions and memory performance. There's no room for misalignment according to the direct access idea. So in comes what we call the Q utilization view, which is sort of established by Coriat in the mid-90s. And his sort of whole thing was nonsense with this direct access view. People can't access the strength of a memory trace. Instead, what they do is they use cues in the environment, maybe in the stimulus, for example. Could be something like the frequency of the word or the brightness or the luminance, something like that. And to the extent that those cues that they use in their predictions are actually truly diagnostic of what they will later remember, then you'll see a weak but nevertheless reliable sort of relationship between their predictions and what they later remember. Now, the nice thing about this view is that it can accommodate dissociations between memory predictions and memory performance, because sometimes the cues that people use are non-diagnostic. And if they're non-diagnostic, that might lead them to mispredict what they'll later remember. Okay? And there are situations where these dissociations can happen. But they are, I would say, not the rule. Okay? So my own thinking on these two issues is somewhat of a hybrid approach. And the hybrid approach acknowledges that memory probably plays a role. Memory signals might play a role in what people predict to remember. But it sort of also allows for the fact that the memory signals that drive people's predictions could be misleading memory signals. They may not be accurate memory signals. And in that case, all you have to do is make that assumption, you can then start accounting for some of the dissociations between memory predictions and memory performance. So it would be nice if we could sort of find some evidence for this. So this is what we did next. And we wanted to know, can mnemonic similarity create an illusion of knowing during study? And what we wanted, the way that we sort of needed to tackle this problem was to create a manipulation of familiarity that people were largely unaware of. And I can sort of talk to you later about why that is, but just take it at face value for now that this manipulation, and we did verify that people were generally unaware of this manipulation, but nevertheless, it works something like this. It's not that complicated. In fact, we actually stole it from Mike Masson, who used this method back in the 1980s for very different purposes. But we nevertheless took the letters of the alphabet, okay, all the keys here, and we divided them into two sets. So we'll call it the orange set and the purple set. So we created essentially what we call set A, which consists of words. But these words are created solely from those particular letters. So we could have caught, quote, chum, you get the idea. And then, of course, we can do the same thing from the letters from set B. And what this allows us to do is to give people some exposure to words, let's say, from one of these two letter sets, and then expose them to novel exemplars at some point later in time and see whether or not it affects their predictions. Okay? So the experiment works something like this. We train them up. They don't have to do much here. They just have to read the word as quickly as possible on the screen. They think it's something to do with reading that we're measuring. Okay? So they only would get exposure to one of the two sets during training. All right? Then immediately following, they would get a study phase. And they say, now we want you to remember these items, and actually we want you to make a prediction in terms of your ability to remember each one of these items on a scale from 0 to 100. We call it a judgment of learning. All right? And then following the study phase, they're then simply given a free recall test. Okay, that's not really what's interesting about, well, I will actually say it will be interesting in a minute. Now, you might be thinking, well, okay, you just manufactured some weird priming manipulation here where you give people some exposure and then you look to see whether or not these items are given a higher JOLs than these items, for example. Are their predictions different? Yeah, fair enough. So what we did was we also had another group of participants where we delayed 24 hours in between the training phase and the study phase. So we wanted to know that, does this exposure here in any way, shape, or form, how long does it last, the effects at the study phase, all right? And then again, you go on and you do your free recall. So I'm going to show you the data first, okay, for the immediate group. And the first bar I'm going to graph here is going to be just the predictions, all right? So we'll call the exposed set during training the primed set, and we'll call the unexposed set at training the unprimed set. And as you might guess, their predictions would be higher for the primed than the unprimed items. That familiarity of those letters through exposure during the training phase, okay, seem to be guiding their predictions. And we've sort of run a lot of studies like this, and this is a very, very robust effect. We almost always see it. But what happens to their memory, okay? In this case, all right, that familiarity at study is actually a non-diagnostic cue, okay? That familiarity is misleading because you can see that their actual memory performance is higher for the unprimed items than for the primed items, okay? So in other words, they are using signals from memory at study to make their predictions, presumably the familiarity of the letters that comprised of those items from the trained set, but that familiarity is misleading. But it nevertheless informs their predictions and creates this dissociation between confidence and accuracy, if you want to think of it that way. This is a little reminiscent of John as well, right? John predicted that he was going to do quite well in the exam, when in fact he did not. And perhaps the reason for that has something to do with misleading familiarity. But we'll get to that later. Now, you might be thinking, great, what about the 24-hour condition? All right? Same basic pattern here. Very strong effect on predictions, although the effect on memory was not significant. And I have to say this memory effect is a little bit mercurial in the sense that sometimes we see the unprimed items are remembered better. Other times we see this null effect here. But we never see the opposite pattern. So true effect size is probably a small increase for the unprimed items, but the key point here is that there's always sort of a disconnect between the pattern of memory and the pattern of predictions. Okay? Okay, so to sum up this section then, mnemonic similarity can induce illusions of knowing where people think they'll remember certain things when in fact it's the exact opposite, or perhaps no difference at all. The last area is sort of a real recent line of work that I've done in collaboration with my former PhD student, Michel Dollois, and it's how do we perceive and act on the veracity of our memory, okay? Now, this last line of research, I think, is nice in the sense that it kind of captures the way that we actually use memory in the wild, so to speak. Most of the time in laboratory settings, we use force report procedures, right? You have to respond to this item. Is it old or is it new? Or in a two alternative force choice, here are two items, pick the new one, or sorry, pick the old one, right? And the idea is that you have to respond in every trial. Now, this is done for good reason, okay? There are reasons for doing it that way. But nevertheless, it's not really how we use memory. In fact, most of the time when we use memory in the real world, okay, we use it sort of in this free report situation. Participants decide whether to volunteer a response to each memory query. They don't have to respond, okay, to every trial. So for example, you might meet an old acquaintance, and you haven't seen them for a couple of years. And so you walk up to them, and the word John might come to mind, but you're not really confident, and so you don't want to say that, so you say, hey there, right? You don't say, hey John. That's an example where you sort of assessed your memory, and you acted appropriately, and you sort of, well, appropriately perhaps. But the idea is that you acted in accordance, right? You used sort of your confidence in your memory to decide to withhold saying the person's name. Another example would be eyewitness memory, right? Where, for example, people are often given the ability to reject a lineup. They do not have to pick a perpetrator from a lineup. So in this case, the person can decide that none of these options feels right. Okay, I'm going to pass. This aspect of memory has not been studied very much at all. There's been a little bit of work on it. Most of it's been done by Asher Koryat. And in fact, he developed this, what he calls the quantity accuracy profile sort of framework in 1996. And it's a brief sort of sketch of how a process like this might work. There's some question gets sent into the memory system. We retrieve some information. Okay, that's the best candidate answer. And then we have to somehow assess the probability of that retrieved answer. Okay, and if the assessed probability is greater than some criterion, then we will volunteer, okay, the response, and if it is less than that criterion, we will withhold that criterion, or that response, I should say, okay? Now, this is sort of captures, again, some basic elements. It sounds a lot like signal detection theory on the surface, but in fact, that idea was largely eschewed by these researchers who actually were quite explicit in their argument that that signal detection theory could not, in any way, shape, or form, capture the pattern of results that they were interested in, all right? The key one of the key outcomes or predictions is that there should be a trade-off between quantity and accuracy, meaning that, okay, the fewer items that people report, of the ones they do report, the accuracy should be better, okay? So the more that, essentially, if you allowed people to withhold the ones they were unsure of, then that should increase their accuracy because the ones that they do volunteer should be the highly confident ones, which, okay, should be associated with high accuracy. But there are also limitations to this framework, and that is, how is it pretty vague on some of these issues, right? How do people assess the probability that the retrieved answer is correct? There's no specification of that. How would you predict the shape of the quantity accuracy trade-off? There's no sort of way of deriving that. So we thought, well, you know what? Maybe Koryat and Goldsmith are wrong. Maybe we can learn something from signal detection theory in terms of this general problem. So I'll walk you sort of through the basic logic of how we approach this problem. And to do so, I have to describe a little bit about the task that we use, which is two alternative force choice. It's a very simple task. You give people some images or some stimuli to encode at study, okay? And then at test, you present them with two items, one of which is a studied item, okay? And the other one is a novel lure. And you simply say, is the item, pick the side, left or right, that has the old item, okay? Two alternative force choice. So how does signal detection theory capture sort of performance in a task like this, okay? Well, again, we have our two distributions. We have our target distribution with some mean familiarity strength, and we have our lure distribution, and I have them here separated by one standard deviation, so our D prime is 1. All right, and on each trial at test, it's sort of assumed that we're going to take one random draw from the target distribution and one random draw from the lure distribution, and we have a memory strength associated with each one of these, and we're simply going to subtract them, okay? And that will give us the distribution of the memory strength values that we would expect to see, if the maximum item was from the target distribution, okay? And you can associate this with the area under this curve, which would be about 76%. So accuracy here is about 76%, okay? But because these two distributions overlap, sometimes you're going to get lure items that have a stronger max or a higher memory strength signal than one of the target items. So in this case, we can also sort of plot what we would expect the distribution of memory strength values to be if the strong item came from the lure distribution. So I have that sort of in pink. You can't quite see it maybe so good, but the basic idea is that you can see, generally speaking, the memory strength value will not be as strong. So once we have these, then what we can do is we can conceptualize the giving people the opportunity to control their response is simply setting a criteria along these strength differences here, okay? So we can see that in this case, we got obviously 76% correct, 24% incorrect. So for example, when given the option to withhold, if people adopt sort of a relatively liberal criterion, meaning that, I'm not going to respond to everything, but I'll, even if I'm not 100% sure, I'll still make a response. I'll pick the one that I think works the best. You can imagine here, sorry, I'm getting ahead of myself here. This is our, I'm just plotting sort of on hit and false alarm space here what the accuracy was, 0.76, okay, and 0.24. That's our forced report accuracy, because that takes all of the trials into account. But if we gave people the option to skip some and they adopted a liberal criterion, we could conceive of that as essentially putting a criterion on this distribution. Anything to the right of it, a difference to the right of it, they would make a response, okay? They would respond with the maximum signal. Anything to the left of that on the difference scale, they would pass. And so you can see now we can calculate what the hits and false alarms would be if they only responded above that criterion. All right? And this is what you would find if you plotted it. It's associated with an accuracy of 79%. All right? So let's make them a little bit more conservative. All right? What do we see? Again, okay, hits and false alarms are decreasing, but because the false alarms are decreasing proportionally faster than the hits, the accuracy is actually increasing. Okay? So what we've just done here is create what's known as a partial RLC curve, because it does not extend from 0, 0 up to 1, 1, but rather it only extends up to the point of what you would expect in the forced choice, where they have to respond to everything, okay? What the hit and false alarms would be in that case. Okay, so do people behave this way? All right, that's the key question here. So at study, we simply gave them some pictures, some scenes, and some objects, all right, and they studied them, and they were brief exposure because people's memory for these things is quite good, so we didn't want ceiling effects. But nevertheless, this is the study phase, and at test, it's a simple forced choice recognition, 2 AFC. There's 3 study test cycles, so they do this process 3 times, and each time we switch it up a little bit. In one of those cycles, they have to do a forced choice, so they have to go through all of the trials. They cannot skip any. In the liberal condition, we give them the option to pass, but only if we say don't, even if you're not sure, that's okay. Only if you really, feel like you're totally guessing, you can skip in that case. And in the conservative condition, what we do is we say, I want you to make sure that when you respond, okay, you're 100% confident that you're going to be correct, okay? Otherwise, don't respond at all. Okay? So those are the 3 study test cycles. Here's the data from the forced choice cycle, okay? So this is the object data, and you can see that performance is quite good for objects. This is not surprising. We can use the hits and the false alarms to calculate a D prime, which comes out to about 1.41. And then what we can do is take that D prime, okay, and then we can use that to calculate the expected RLC that's associated with a D prime of that magnitude. And then the question becomes, well, what happens now when we plot the hits and the false alarms for our 2 free report conditions? According to signal detection theory, they should fall along this line, okay? And they fall pretty well along the line, not perfectly. So a way to quantify that would be just, let's fit the best fitting RLC, okay? And then let's take the D prime associated with that, which is 1.36, and then divide them for a ratio, and you can see the ratio is about 0.96. So it's a pretty good match between what you'd predict and what we found. Okay? And the same thing holds, well, maybe not quite as tightly, but the same thing holds when we look at the scenes. Okay? maybe the ratio is a little bit lower here at about 0.92. But nevertheless, it does seem like people are doing this pretty efficiently. When we give them the option to withhold their responses, they're doing so in a manner that would be predicted by signal detection theory. Now, we were a little bit sort of put off by this because it was sort of a little bit, we couldn't explain exactly why the performance here was a little bit lower. So we thought, let's replicate this where we just use just scenes. So that's what we did in the last experiment here. All right, so again, they were just studying these scenes, and then at tests, okay, we manipulated the response criterion slightly differently. Okay, here's 2 items here. Here's the sort of the way that we did it. So in the forced choice condition, they had to make a response on every trial, and they just simply rated their confidence from sure, definitely left to definitely right, and they could not skip. In the liberal condition, they could use all the confidence ratings, but they also had the option to skip. Okay? So if they're really unsure, they could go ahead and just hit the space key to skip. In the medium condition, okay, now we grade out the possibly options, and so that now they either had to pass or they had to answer with a probable level of confidence. In the conservative group, okay, we left only the definitely options available, otherwise they have to pass. So in other words, we're getting them to, again, respond more conservatively just by limiting which response options are available to them. Well, the data behaved quite nicely in this experiment. You can see here that the points fall quite nicely along the line that you would derive from the forced choice data. And when you do the math and you get the ratio, it comes out to about 0.95. Okay? So I think what this suggests is that you can think of the free report largely as sort of a signal detection process. And the predictions that you would make largely are borne out by the data, although it may not be 100%. It's pretty darn close. And it's kind of interesting, maybe potentially interesting further avenues to sort of explore that difference a little bit to see maybe there's some source of inefficiency that people are exposed to when they're given the option to decide to choose or not to respond. Okay? So what's the nature of that inefficiency? All right. So to sum up, the take-home point that I want to sort of make here is that we need to consider, if you want to understand memory behavior and memory performance, I think it's helpful to consider you need to understand to some degree the strategic or learner-centered aspects of it, what we call meta-memory. But on the other hand, if you want to understand meta-memory, I think it's also you have to understand memory. And I think the last sort of line of research sort of made that point. Metacognitively speaking, or at least I should say giving people the ability to withhold, presumably would, I think most people in the field would say that's a metacognitive problem. You have to monitor in order to decide whether or not your response is correct, and that's a metacognitive process. So if you're not confident, you're going to withhold, and if you are confident, you'll volunteer. Okay? But I think what this sort of work demonstrates is that you can actually understand that from a purely memory perspective without invoking any concepts of metacognition or monitoring or anything like that, unless, of course, you assume that metacognition itself is built into signal detection theory. Because signal detection theory does give a mechanism for accounting for confidence. So insofar as confidence is a metacognitive phenomenon, you could make that claim as well. So just to sum up here, learner autonomy benefits memory encoding. Strategic use of veridical mnemonic information can mitigate false memory. Okay? Misleading mnemonic signals can drive illusions of knowing. And mnemonic information can serve as the basis for monitoring and control of retrieval in free report situations. So lastly, just to finally return to sort of our friend John here, perhaps the issue with John is not really a meta-memory problem at all. Perhaps his meta-memory is fine, but rather what his problem is just bad memory. Sometimes he might think he got the right answer, okay, because it felt familiar, and that misleading sense of familiarity would lead, sometimes could be very strong, which would then lead him to think with confidence that he answered the question correctly. So I'm not saying there is no metacognitive contribution here. I'm just offering sort of an alternative perspective on the problem, and that memory problems would manifest in much the same way as problems with meta-memory, with intact memory, if that makes sense. Okay? So I'd just like to thank everybody who's contributed to this work, the graduate students past and present, the honors thesis students currently, and yeah, everybody for listening. So thank you. Yeah.
So I was wondering if it was known if this kind of switching between strategies for remembering has a cost. If you just use one strategy, you actually kind of get better and have a bigger benefit than if you switch around.
So you're referring to like the different, like,
The 6 different strategies.
oh, the 6 different strategies. Possibly. That's a good question. What I can say, though, is that because we had our yoked control condition, they would have switched strategies to the same extent as the people in the strategy choice group, right? So I don't think that strategy switching.
Is there a correlation between how much switching and how well they did, like negative correlation?
It's a good question. We haven't looked at that. That's something we could do, though. We have the data to do that. Yeah. Yeah. Could be. Yeah.
Related to that, did you look at memory performance in the various strategy conditions to see if one was better than the other?
Yes, we did verify that. And so the strategies that a priori we would have considered to be effective, like, you know, creating sentences or mental imagery, were indeed did produce better performance than the ones that we a priori would have thought to be ineffective, like rote repetition, for example. Yeah.
Also related, I was wondering, do you guys look at their music, keeping track of how often the people switch between strategies, or how often they like stop their time? Like maybe they did it like half the time on the
Yeah, so what we did do was, one analysis that we did do, I forgot to mention when Sagal was asking her question, was we binned the study phase into 10 bins, okay? And what we did is for every bin, we looked at what's the proportion of times that they used an effective versus an ineffective strategy. And we did that separately for each of the 2 groups. And what you find is that, generally speaking, the ineffective strategy use is highest at the beginning, and that over time they start switching away from ineffective towards more effective. But I don't think we did the analysis to look to see within each category are they switching. If that makes sense. Yeah.
Nice talk, a lot of interesting stuff. I'm curious, you made a comment about the last bit of work we were talking about, where you can withhold the memory that the people, the investigators who invented this paradigm were consistent or single detected not explain this, and I was really surprised by the statement because I thought the dominance. And there's work like in animal literature, I think it's mostly pigeons and sharrows and monkeys and stuff. The monkeys, not in memory, but in discrimination, they seem to act as though they have metacognition.
Mm.
That they will withhold their responses when the discrimination is hard.
Mm.
And it's perfectly consistent with signal detection theory. And you don't have to think that they have metacognition. All you have to do is say you're maximizing your reward based on the strength of the perceptual signal. And so I'm wondering, like, what if people still think, I mean, obviously after your look at the can't think, why would this not be consistent with an idea that people have access to some sort of continuous measure of memory strength? And when it's weak, you withhold your response. And when it's strong, one way or the other, you can say, I know that or I don't.
Yeah, it's a good question. So if you, I'm not suggesting you go back and read the Coriat and Goldsmith paper, but in that long paper, they do sort of describe sort of their issues with signal detection theory, and they say that basically the reason why they eschew it is because essentially signal detection theory cannot accommodate situations where confidence and accuracy dissociate. And they point to many scenarios where they can see that dissociation. And so therefore you can't, they think of it as there's a separate sort of, there's maybe a memory strength signal, but there's a separate process of monitoring that, and you could be more or less accurate at monitoring the strength of that signal. So there's a separate sort of like part 2, right? It's not just the memory signal itself. That's the argument that they're making. I always sort of, I guess I wanted to know, do we have to make that assumption? Yeah.
They're saying there's a memory strength signal, but sometimes some people can't monitor.
That's right. So there's a separate monitoring process. So sometimes the memory signal itself could be perfectly intact, but for whatever reason, they perceive it as, let's say, it's a noisy perception process where they might perceive it as weak. And so that would mimic a weak memory, like, that's their point, yeah.
One question about the third cell.
Sure.
Where you had the keyboard items. And my question is really, we've got two results. One is people are giving higher judgments of learning for the primed items.
Mm.
And they're in the ideal case, their memory performance is worse. Do you think those two findings are like causally related? Are these right?
We've thought about that. It's a good question. So we did think for a while that on some level, obviously the unprimed items would be perceived as more difficult. Sometimes difficulty is good for memory. The less familiar, you could think of them as maybe there's sort of a greater novelty signal associated with them. Novelty is good for episodic memory. So it could be something akin to like a desirable difficulty-like effect that we're seeing in that situation. I hedge a little bit only because the effect tends to, if we did a meta-analysis across probably, 10 or 15 experiments like this, we'd probably find that there's a reliable small effect of a difference for unprimed being higher. But it's hard to sort of really go to the bank with that. But I would imagine that the same process that drives the JOL effect also drives the memory effect.
I have this crazy question that's really probably very basic, and everybody else in the room probably knows the answer to this, but it's just that I don't really know this literature at all. When we think about false memories, is that usually more to do with issues with encoding, storage, or retrieval? Like, what do people think is the main reason for false memory, and what is the evidence for that?
Yeah. Well, certainly in the DRM paradigm, for example, I think if you surveyed the field at broad, they would say probably the most common answer would be all of those related studied items, they all activate the same theme, and that theme becomes highly active in memory, or, in mind, and then therefore, at test, when you see that critical lure, that theme is readily accessible and you mistake it, right? I think that spreading activation idea is probably the most common idea of it. But other people have talked about it as basically being like, no, you don't need to think of it necessarily that way. You just encode the information, veridically as to what it is, and then when a similar probe like Crown comes along at test, well, it's going to activate to a large extent all of those memory traces that it shared similarity with, that had similar features with, and that some similarity signal is what's returned out of memory, and ultimately drives sort of the endorsement of the Crown as a false alarm.
But in the real world, like if you're thinking about a lineup and some expert witness saying, that's the guy who shot him or whatever, they don't bring in people who look every which way. They bring in people who look a lot like the suspect, right?
Yep.
They're not really, so they are bringing in similarities. Like we're constantly in the real world trying.
Yes.
I'm just sort of trying to understand the why.
So in the eyewitness literature that you bring up, there's a lot of work done sort of in that area. I can say for sure that, yeah, you're right in the sense that there's all the people in the lineup are all matched to the description that the witness provides, so there's some similarity. There's been some people suggesting that you don't want the lineup to be too similar. You don't obviously want it to be totally dissimilar where the suspect sticks out, but you don't want it to be too similar because you want there to be enough features that are not shared that you can use to sort of diagnostically to determine who the suspect was. So that similarity can be leveraged in some ways if you can discount the shared features and just hone in on features that are diagnostic. Some people have talked about that in the eyewitness literature. But generally speaking, in the eyewitness literature, I think the more modern thinking about it is that eyewitness memory is actually pretty good. There's not a lot of false memory unless you don't do the proper procedures when you're testing memory. And generally speaking, there's a very strong relationship between confidence and accuracy, with eyewitness testimony, especially for the high confident responses, the people that choose a suspect from the lineup with high confidence. Those are almost always correct unless memory's been tested multiple times, or there's some other contaminating influence like exposure to misinformation or something like that in between. Yeah.
Thank you for a great talk, Chris. I know this is sort of was a side note of your research, but for the students that are here, my ears perked up when you said that there was, you know, the highest sort of accuracy strategies for that these participants used were sort of the active recall, where they're using the word in a sentence or they're encoding it in a sentence in that way. But then also your results showed that whatever you sort of chose as your strategy, so long as you stuck to it, like you had that free range of choice, you were more likely to be accurate. So I guess what I'm trying to ask is, do you know which would be a better or more faithful strategy to use? So, for example, if I'm a student that is influenced by, you know, all these academics in the field that are saying, oh, don't recall or don't try to memorize things by just, you know, saying it over and over again, but that's the strategy I've been using, or vice versa. Is it better to switch? Is it better to stay faithful to my strategy?
I think, you know, I think if you think that, like, on some level, what we think might be happening, and there's alternative explanations, I'm not saying this is the correct one, but one thing that could be happening in the first set of experiments I showed you is that certain information calls for certain things. So in other words, the best strategy for encoding that piece of information may well be dictated by what that information suggests to you and who you are. So it's in some ways personalized to you. It's not suggesting, generally speaking, yes, if you encode it, you know, with mental imagery and you do the effective things, that'll give you better performance, and we see that too. But I think what it does suggest is that there is some room sort of to tailor it to sort of fit what you think would be best for you with that information. Yeah.
Many years ago, I took a course with Arnold Buss. Very eccentric social and personality psychologist. And he wrote a book, I think, called Personality or Social and Personality Awareness or something. He taught a course on it. And the whole set of experiments, his thesis was that you ask most people, these undergraduates at the University of Texas, to sort of tell the experiment about themselves, what are their psychological traits and so on. That many, maybe a majority, will give accurate descriptions that their friends and their family members will do the same thing. But there are a lot of people, I mean 40%, who give random answers. I mean, who basically have no insight into their own psychological traits. They give the judgments of themselves, and it's as accurate as if they were given to another stranger. And he did some experiments to show it wasn't that they were just BSing or whatever, because he could manipulate it. And so he said that social awareness and introspection was a skill and maybe a trait. And some people just allows it. I'm wondering if memory or metacognition is like that. If there are some people in your experiments who just, I mean, the idea of thinking about their memory or their thinking is bizarre.
Yeah, I mean, yeah, we haven't really gone down sort of the individual differences pathway on this. There have been people that explored that. Some people sort of say that there is like a general metacognitive ability that they can measure that's independent of like the first order cognitive ability. I don't know, I'm not as familiar sort of with that literature. My own thinking on it is I think they're connected. I think a lot of what we call metacognition, there might be sort of that reflective component, but it does reflect, I think, a lot just the content of the first order thought. And sort of when you use memory or something like that, a byproduct of using it is sort of a qualitative assessment that sort of comes along with, like, you know, how quickly did that come to mind? And that's a pretty diagnostic cue of whether it's correct or not. Now, it can be hijacked, which experimenters are really good at doing, but generally speaking, it's a pretty reliable cue as to accuracy.